In this work, we introduce a visualization system that understands and compiles silent error propagation. HPC system is becoming more and more powerful. The size of the computation unit continues to shrink. The total number of the computation unit increase. However, these threats will lead to a phenomenon that an error occurred during a computation will also increase dramatically. This error, such as soft error, will lead to different outcomes such as crash, which an error occurred during the computation and lead to program crash, or mask, which error occurred but its impact is too small or mitigated by the program logic, and at the end it doesn't affect the computation's outcome. The worst case is silent data corruption, which an error corrupts a computation and it propagates to a program's final output without warning. Understanding the silent error propagation in a program is important to improve the program's resiliency. To mimic the soft error, HPC researchers often use fault injection tool which manually inject an error during the computation and observe the error propagation. Here, as an example, we use a function that performs the vector multiplication to demonstrate the fault injection process. In the unrolling loops, the fault injection tool selects the sum variables and pick one of its bits and flip it to perform the fault injection. Fault injection campaign is a set of fault injection testing which often randomly select different variables and bits. In comparing, the exhaustive fault injection campaign will literally test all select data variables and bits. In our system, we use a bit flip plot that gives a summary of different fault injection experiment statistic outcome. After an error is injected, the error will propagate to the subsequent computations. The overall propagation data can be considered as a high-dimensional time series data, and it can be visualized as a temporal data visualization. Each fault injection set has its propagation data. Comparison will help to reveal variable insight of a program's resiliency and vulnerability. In this system, we use dimension reduction, which project high-dimensional data into 2D space to have an overview of the similarity of different error propagation. Fault tolerance boundary gives the maximum error that each fault injection set can tolerate. In the same cases, each step have a maximum error that the program will tolerate without causing the program generate silent data corruption. And the final boundary can also be visualized as a temporal visualization. Here is the overview of the system that we designed to understand and comparing silent error propagation. The first view is the fault tolerance boundary visualization, which is a two-layer temporal visualization that shows the resiliency of the program over time. The propagation similarity view gives an overview of the similarity between different error propagation. The bit flip summary views give an overview of the impact of each bit in different program components. The propagation view coordinates with the source code view and data log view to understand the detail of error propagation process. Here we have a quick demo to demonstrate how each views interact with each other. User can manually adjust SDC thresholds. The overall visualization will change based on these values. If we change the SDC threshold to large values, from the boundary view we can see that the SDC ratio in different locations kind of decrease. From the bit rate summary view, we can see that even a lot of exponent bits does not cause any significant silent data corruptions. In the opposite, if we change the SDC ratio to a small value, from the boundary visualization, we can see that the SDC ratio in many locations increased dramatically. In the bit rate summary view, we can see that some of the mantissa bits start to cause silent data corruptions. From the boundary visualization, user can select a time interval and examine the fault injection outcome in these regions, or compare the similarity of error propagation start from this region. User can also select a set of error propagation from the propagation view. From the fault tolerance boundary view, we can see that when these errors start propagate. From the bit rate summary view, we can see that where those errors start to propagate. Here we select a large set of error propagation experiments. From the boundary view, we can see that those error propagations start all across different locations of the program. From the bit rate summary view, we can see that those error propagation was caused by bit flip in the lower mantissa bits and some of the exponent bits. which further confirm information that most of the anticipate does not cause significant error propagations. User can also select a component from the bit-free summary view. All the error propagations start from that region will be displayed in the propagation visualization, and the fault tolerance boundary view will show when these errors are injected. At the end, user can select a non-monotonic error propagation cases from the fault tolerance boundary view. The error propagation view will provide a detailed error propagation process. Here we demonstrate a cases that a large error is injected in the computation. However, the error is mitigated by the program computation. To deal with the scaling challenge, the graph visualization can collapse part of the nodes and manually adjust those locations.